Hello, welcome to bonding continuation, focusing on formal charge and VSEPR. All right, so looking back from dot structures, we have this concept of resonance. May be familiar, may not be familiar, but ultimately, resonance is invoked when you have more than one valid Lewis structure that can be written. So kind of lots going on here. If you are asked to show all resonant structures, then you need to do that. If you're not, then don't worry about it. So first example, we'll look at benzene. As we can see, based on the left image and the right image, the movement or the location of these double bonds is what the difference is. All atoms stay in the same place. Total number of electrons hasn't changed. The location of the double bond is what has changed. And then since it's constantly moving back and forth, the actual structure is technically an average of these two. So all the bonds within the benzene ring, the carbon-carbon bonds, they're not fully single, they're not fully double. They're an average between the two. So the bond lengths in the ring are actually all the same. Even though you see double bonds and single bonds, technically they are all identical because it's an average between the two structures, where each bond 50% of the time is single and 50% of the time is double. Questions on this? Okay. So, as we kind of just alluded to, resonant bonds are shorter and stronger than single bonds, but they're also longer and weaker than double bonds. Again, this comes about because the electrons are constantly moving. They're constantly changing their location. Questions? Okay, here's just another example of ozone, showing the same thing, atoms in the same place, but double bond in a different place. Technically, individually, neither structure is correct. Sometimes they will draw both of these oxygen bonds with a solid line and then a dashed line above it. You don't have to do it. Don't worry about that part. All you guys need to do is just draw the dot structure. All right, when we get into polyatomic ions, just another example. Here's a carbonate ion showing resonance. I know it looks like you've rotated it 3 times, but technically those are different oxygen atoms. Therefore, they are different structures in that sense of the location of the double bond. Acetate ion, again, notice everything's in the same place, just the movement of the bond. Questions on resonance? Okay. All right, so formal charges. We have an equation we have to use. Now, the purpose of formal charges is when you have resonant structures, the goal is to determine which of those resonant structures is the best one. Now, a couple of the examples we've seen, they're mirror images, they're all the same, so all of them are fine. But sometimes you come across where the number of resonant structures, there are some differences that can make one structure better than the other. So, simple equation, your formal charge on every individual atom within a structure is just the number of valence electrons in the neutral atom minus unshared or lone electrons on that atom plus half the number of shared electrons. Simple equation. We'll go through a couple examples to check that out. So, in order to evaluate our Lewis structures, ultimately we want formal charges as close to 0 as possible. That is the ideal situation. So when you put all your formal charges onto your Lewis structures, you're looking for the structure that has the most zeros as possible. If there are any negative formal charges, they should be, or they're expected to be, on the most electronegative atoms. So again, got to know the trend of electronegativity that we alluded to last time. And lastly, the sum of your formal charges has to equal the overall charge of the ion or molecule. So if it's neutral, they'll add up to 0. If it's an ion, they will add up to the actual charge of the ion. For example, here's the sulfate ion. Now, the structure in the middle, yes, you could put the double bond in 4 different places, but from a formal charge perspective, they'd all be the same. That's why only one is shown. So of these 3, which one do you think fits the above criteria the best? Think about that one. Let's mark it as left, middle, or right. Make a note on your paper. Okay, so the answer should be the one on the right. It has 2 negatives and no zeros. The other 2 have positives. Positives are bad in that sense. So the sulfate ion spends the most of its time looking like the right image. Questions on this? Okay. So here's an example, carbonate ion. Again, 5 choices. Which one do we feel would be the best Lewis structure for the carbonate ion? Make your note of A, B, C, D, or E. Okay, hopefully the answer we got was A. Questions? All right. Nitrogen dioxide. This one's kind of pretty straightforward. The one on the right, all zeros, is the best case scenario. Questions on formal charge? All right. So the localized electron model is pretty self-explanatory. Local, meaning, you're from San Ramon, you are local. Electron pairs can be thought of belonging to pairs of atoms when they're bonding. So if 2 atoms in a covalent bond are sharing electrons, those electrons belong to those 2 atoms. Lone pairs on any given atom only belong to that specific atom. The problem with this model is resonance points out a weakness because, as we saw, there was double bonds moving around. Well, those movable electrons that are jumping and kind of free-flowing throughout the molecule, they're called delocalized electrons. They have no home. They're a bum. So they're able to move around and jump between bonds, between different atoms, hence resonance. That's why they're delocalized. That's why it's kind of a weakness to this model, because if it's a double bond, you would think that all 4 electrons belong to those 2 atoms that are holding on to that double bond. But when resonance is able to occur, it doesn't actually work out that way. Questions? All right. All right, back to our friend VSEPR, valence shell electron pair repulsion. This should be mostly familiar to everyone. So our goal, again, is trying to create a model, a dot structure, where we're minimizing electron pair repulsion. Now, an electron pair can be both a bonding pair as well as a lone pair of electrons. So pretty simple to predict the structure. We want to draw our Lewis structure. We all know how to draw Lewis structures by now. We want to make sure we put our bonds and our pairs of electrons as far apart as possible. Note you are making a 2-dimensional structure, and that is perfectly fine. Well, based on the positions of the atoms and electron pairs are shared, we can figure out, what kind of shape is going to be created. And how we do that is we're going to use the Axe formula. I know some of you may be familiar with this, and some of you may not. So we're going to look at it. Our Axe formula, pretty self-explanatory. The benefit of it, you guys are drawing a 2-dimensional dot structure. Molecules are 3-dimensional. It's a very challenging thing to see a 3-dimensional shape when looking at a 2-dimensional drawing. So the Axe method allows us to relate an Axe formula to a shape. So it doesn't matter what the molecule is, whatever Axe formula that it gets, it'll always be that same shape depending on the formula. So A represents central atom, easy enough. X represents the number of sigma bonds, also known as single bonds that are attached to your central atom. Now realize multiple bonds, a pi bond, also called a double bond, or a triple bond, still counts as one thing bonded. So single, double, triple bond is still one thing bonded to your central atom. And then E represents lone number of electron pairs on the central atom only. Students tend to look at their entire structure, they see a bunch of lone pairs everywhere, and they can add them all up. No, it is only on the central atom. Lastly, if we add up X plus E, we get this thing called the steric number, which will play more of a role when we get to hybridization. Questions? Okay. So this chart, don't copy it. There's one online on my website. The steric numbers we have are just 2 through 6. There is no steric number 1, and we're worried about 2 through 6. In the middle, we have the electronic geometry. So if we look at the number of pairs around a central atom, not caring if it's a bonded pair or a lone pair, represents the electronic geometry. All of these electronic geometries correspond to all of these Ax formulas that do not have lone electrons. So if there's 0 lone electrons, it's all bonded pairs. The electronic geometry and the molecular geometry will be the same shape. The minute we start adding lone pairs, that's what the E is on this chart, the shape begins to change. So when we get to AX2, again, carbon dioxide, pretty self-explanatory, 180 degrees. Yes, you need to know the angles. Trigonal planar. As an example, BF3. Again, makes a triangle in one plane, 120 degrees. But then when we get AX2E1, it becomes bent. So again, the red shape here, the red letters represent the molecular geometry. We're at the very top, trigonal planar. That is the electronic geometry and molecular geometry if there are no lone pairs. AX4, going to be tetrahedral. Notice no lone pairs. But the minute we get a lone pair, we're now trigonal pyramidal. We have a different bond angle, 107.5. Or we get to AX2E2, bond angle gets smaller. It's now a bent shape. So any molecule, AX3E1, is always trigonal pyramidal. The formula tells you the shape every single time. So trigonal bipyramidal, AX5, got 2 degrees. If we add a lone electron, we get a little seesaw, those things in the playground you can sit on. And then AX3E2, it now looks like a T. I know it's sideways, but it does look like a T. Again, 2 bond angles again. And then AX2E3 ends up being a linear shape. So again, the formula corresponds to the shape, regardless of the molecule. And our last one, AX6, octahedral. If we have 1 lone pair, we're now a square pyramid. And if we have 2 lone pairs, we're now square planar. Again, the whole purpose of these shapes is to make all electron pairs as far apart from each other as possible. Questions on VSEPR? Okay. So, little reminders. The rest of the slides here are just kind of basic information and reminders on dot structures. So I'm going to stop it here, but you guys can by all means pick this up on your own and go through these last few slides on your own. Again, all reminders, basic things, and we'll go from there. All right, thank you. So again, the octet rule, dealing with atoms when they form bonds, want to have 8 valence electrons. That is the goal every single time. So looking at 2 fluorines, they come together, share that electron, and therefore they all are going to have 8, is what they want. Second period elements, carbon, nitrogen, oxygen, fluorine, they will always observe the octet rule. Think about the honk rule. Hydrogen wants 1 bond. Oxygen wants 2 bonds. Nitrogen wants 3 bonds. Carbon wants 4 bonds, or any variation of those numbers. Boron, beryllium tend to have fewer than 8. They are exceptions to the rule. Boron is fine with 6. Beryllium is fine with 4. So just kind of a FYI of exceptions. Third period and heavier elements. They can exceed the octet rule by having expanded octets. The common ones are phosphorus having 10, sulfur having 12. But again, anything in the third period and below can go expanded octet. Now, how do they do this? It comes with hybridization, which we'll get into later on. When you're writing Lewis structures, I have a set of rules coming up. Ultimately, at the end of the day, satisfy your octets and then make everything work at the end of the day. You can always move electrons around and atoms to make sure things get what they need. So looking at water from a octet rule perspective, 2 hydrogen molecules, 1 oxygen molecule, giving 2 water molecules, we can see oxygen has its 8, hydrogen has its 2, the duet rule, and everything is satisfied. Again, Lewis structures, we know them, nothing new there about how to do them. Here are the rules that I go by in creating dot structures. So please check it out, pause this, write them all down, make sure you follow the same rules, but it's a very systematic way of doing it. And then, again, a double bond, making sure we realize there's 4 electrons, 2 pairs of shared electrons, and a triple bond is just 6 electrons or 3 pairs. Thank you very much. Have a good one.